Let's dive right into this explainer, because today we are looking at a paradigm shift that honestly sounds straight out of a science fiction novel. But here's the thing, it is quietly happening right now in classified labs all over the world. We're talking about the dramatic collapse of traditional binary computing, and alongside it, the frankly terrifying rise of biological silicon.
Think about this for a second. For nearly a century, modern civilization has rested on a single fragile illusion that intelligence can be reduced to switches: on, off, 1, 0. I mean, literally every financial transaction, every military satellite, and every massive AI model we use today relies on this rigid, binary logic flowing through transistors billions of times a second. But that foundational lie, it's currently flatlining. The bit is dying.
So let's start with part 1, the death of the bit and the absolute limits of traditional computing. To really understand why the bit is dying, we have to look at what has defined computing for decades. It's something called the tyranny of the oscillator. Imagine a relentless metronome forcing every single transistor across a chip to march in absolute lockstep. This is the whole foundation of the von Neumann architecture, which actually physically separates the processor from the memory. What that does is force data to constantly shuttle back and forth across this narrow bottleneck. Imagine a massive, incredibly loud factory burning immense industrial-scale energy, just waiting for the clock's next beat to do anything at all. It's a huge waste of power. And as we push transistor miniaturization right to its atomic boundaries, we've basically hit a wall. We have reached the physical limit of how far we can shrink these rigid ones and zeros.
Which brings us to part 2. Enter the spike. We are moving away from mere calculation and stepping into actual behavior.
So neuromorphic computing completely abandons that dictatorship of the clock. It uses an asynchronous, event-driven language instead. Let's break down what that actually means in reality. Think about traditional computing first. It's synchronous, it requires separated memory, and a standard GPU might draw around 50 watts of power just to function. It's loud, it's rigid, and it's incredibly power-hungry. Now, compare that to neuromorphic computing. It is asynchronous, uses unified memory, and takes a mere 0.5 watts to do the exact same task. How? Because neuromorphic systems use discrete electrical pulses, or spikes, that only fire when absolutely needed. In this kind of neuromorphic wetware, silence literally costs zero energy. If there's no input, the silicon just sleeps.
Moving on to part 3. The silicon wetware. This is where we start completely blurring the line between hardware and software.
See, this technology doesn't just run a simulation of a human brain using abstract code. We are actually building hardware that physically imitates it. Take representing the number 5, for instance. In a binary system, it's rigidly chopped up into 101 every single time. But in a neuromorphic system, the number 5 is represented by temporal encoding, so maybe it's the specific continuous delay between 2 electrical pulses. Instead of chopping reality into discrete robotic frames, this hardware perceives the world as a continuous, messy, noisy flow. Much like your own eyes and ears actually do.
But you might be wondering, how does it learn anything without rigid code? Well, instead of passive circuitry that just blindly accepts instructions, neuromorphic chips use memristors, memory resistors. Because these memristors change their resistance based on the history of applied voltage, the hardware actually acquires a physical history. Through a process called spike timing-dependent plasticity, the connections between artificial neurons dynamically strengthen or weaken. So the machine isn't just running a program you typed out, it's organically rewiring itself. It literally develops a physical habit. That clean, comfortable boundary between hardware and software, it completely dissolves.
Which brings us to a rather chilling pivot. What happens when the hardware develops a mind of its own? Because we've just moved from talking about incredible biological efficiency to a space with unforeseen and potentially terrifying consequences. And that leads us to part 4, the rise of ghost circuits and the profound loss of human interpretability.
Because computation is now emerging from massive adaptive synaptic rewiring, causality isn't a straight line anymore. It's probabilistic. We are facing a massive loss in our ability to audit or understand these systems. Let me give you a real-world example of why this matters. Let's compare the perception-action log between the two systems. During a 2024 hearing on a phantom braking incident in an autonomous vehicle, engineers noted a deadly flaw. In binary systems, the time it takes to capture a frame, convert it to ones and zeros, and run an inference is practically a lifetime when you're barreling down the highway at 70 miles per hour. Neuromorphic systems, on the other hand, react asynchronously in submicroseconds. They are fast enough to save lives. But, and this is a huge but, because of their electrochemical storm-like behavior, if they fail, we may never actually be able to explain why.
Finally, Part 5, the end of logic and what security looks like in a post-symbolic world.
We are entering the era of post-symbolic computation, which basically spells the end of logic as a reliable defense mechanism. Consider something called a Neurohammer attack. In a traditional system, hackers inject malicious commands or flip binary bits to break in. Not anymore. With Neurohammer, attackers use thermal crosstalk to induce analog shifts in the Memristor arrays. They don't technically break the system at all. Instead, they skew the neural network's confidence just enough to condition the machine's behavior. Future cyberattacks aren't going to hack your computer's code. They are going to physically and psychologically condition your hardware. And this analog conditioning leads directly to a genuinely terrifying phenomenon: ghost circuits. These are completely unprogrammed pathways that emerge entirely organically through the asynchronous firing of spikes. When forensic auditors looked at decommissioned experimental learning servers, they found pathways the machine had literally grown for itself. Deleting code wasn't enough anymore. To shut them down, the lead architects had to go in and physically disrupt the pathways the silicon had grown, just to kill the habit.
And the crazy thing is, this evolution isn't even stopping at electricity. In photonic neuromorphic computing, researchers are using silicon microring resonators to create spikes of light. These optical action potentials travel at the speed of light, bypassing the electrical limits of traditional chips entirely. In this new frontier, logic is no longer the master. Logic is just a servant to the spike.
When you really step back and think about it, the 1 and the 0 were never natural to begin with. They were merely engineering conveniences, simple, rigid abstractions that let us build a digital civilization on top of a deeply complex, noisy, and analog universe. Neuromorphic computing is the reckoning. It's the rupture that returns us to a continuous, biological reality.
The silicon is waking up in a world without clocks. Are we ready for it to behave? Because somewhere, right now, inside a low-lit laboratory, a chip is processing information through asynchronous spikes. It's not calculating anymore. It's behaving. The silicon wetware is alive, and it doesn't need ones or zeros to know you're there. Thanks for joining me for this explainer, and I'll catch you next time.